Hey programmers, Alvin here. Right now I want to work through this fib problem. Of course, we're referring to the classic Fibonacci sequence. This is a really important, computer science problem, and to me it serves as the foundation to really unlocking a few harder concepts down the line. So even if you've done this fib problem before, it helps to review it together right now. We're going to see this core pattern show up a lot during the course together. And so let's start by understanding what we should do in this problem. Well, we know that the Fibonacci sequence has a few certain seed values. We say that the first number of the sequence is 0, and the second number of the sequence is 1. And then to generate further numbers of the sequence, we just take the sum of the previous two. In other words, I can take 0 plus 1, and that gives me the next number, 1, right? So the sequence starts 0, 1, 1. Then from there, I continue this pattern, right? I can take the 1 plus 1, that gives me 2. I can take the 1 plus 2, and of course that gives me 3, and so on and so forth. And of course I can generate the sequence of infinite length in this way. And so overall, in this rendition of Fibonacci, what we want to do is actually return the number at the specified index of the sequence, right? And so a really key insight about the Fibonacci sequence is to generate any particular number of the sequence, we must know some other numbers of the sequence, right? I can get 8 by just doing the previous 3 plus 5. If I wanted to actually formalize this problem a little bit better, what I'll have to do is understand that these numbers I have listed are really the elements of the sequence. And of course, I can assign some indices to those elements. So up top, I'll just label these increasing by 1, of course, but starting at 0. So I can say something like, hey, the 0th number of the sequence is 0, and the first number of the sequence is 1. And also the second number of the sequence is 1, and so on and so forth. So kind of jumping ahead a little bit. If I look at this particular position, what I see is, all right, it seems to be that the 7th number of the Fibonacci sequence is exactly 13. That's going to be overall the shape of this problem. All right, so how can we go about solving this one? And so for this particular approach, what I want us to do is actually work through this one recursively. I think the iterative solution is pretty straightforward, but I'm going to force us to solve this one recursively because it's going to help us learn some new topics along the way. So we'll kind of stick to a recursive mindset, and if you hate recursion, too bad, you'll learn to love it right now. And so looking at a particular example, let's say I wanted to figure out how I can come up with the solution for fib of 6. In other words, the 6th Fibonacci number is exactly 8. And so what I can start to do is figure out how to break down this problem. I know in general, to generate the 6th number of the sequence, I can take the 5th number and add that to the 4th number, right? It's exactly the rule of the Fibonacci sequence. Let me try to visualize this one a little bit better. So I'll represent the problem, fib of 6, using somewhat of a tree. And I'll represent an instance of the problem as a node of this tree. So I have my top level problem of 6. That'll be the root of this tree. And this is a really important way to actually visualize recursion because it really shows us how we're going to utilize our return values and reconstruct our final answer. So if this is a new pattern for you, don't worry, we'll walk through it pretty slowly together. And so now that I have this root of 6, I have to figure out how do I break down this problem. Well, like we just said, to solve fib of 6, what I need to do is break that down into fib of 5. So that'll appear as a child of that 6 node. In the same way, fib of 4 also needs to be solved to solve our main problem over here. And notice how I have these, children nodes, of course, below the fib of 6, right? As I go downward in this tree, I should be getting smaller and smaller numbers in blue, right? That would represent a smaller problem. Because I know once I have a small enough input in blue, then I would have somewhat of a base case, kind of inherent to the Fibonacci sequence. So let's take a closer look at this 5 node over here, right? This node represents the problem of fib of 5, right? What is the 5th number of the sequence? And I know in general, my pattern is, all right, if I want to calculate fib of n, then I take the sum of n minus 1 and n minus 2. So I'm just going to apply that pattern to this 5 node. In other words, on 5's left, it's going to have a node of 4, and on 5's right, it's going to have a node of 3, right? Doing a minus 1 and minus 2 respectively. And it's a similar trend for the 4 node on the right-hand side over here, right? It's going to have 2 children, of course, doing minus 1 on the left and minus 2 on the right, giving 3 and 2 respectively. So let's keep applying this pattern. What we're going to do is fill out the next level of the tree until we can't fill it out anymore. What we have to notice here is when it comes to actually building the full tree, we have to stop at certain nodes. In other words, once I have an instance like 0 as my input to this little subproblem, I can't actually shrink that problem size any further. So I'll highlight all of these nodes whose input is 0, right? That represents the 0th number of the Fibonacci sequence. And something inherent in the problem is I can't really break that problem down any further. I know that for those particular nodes, they ought to return 0, right? Because the 0 number of the Fibonacci sequence is exactly 0. So in green, I'm going to represent the result or the answer to those subproblems, right? I'm going to put their answers above the problem itself, right? So I'm trying to be very, very particular in my drawing. I'm always going to write a return value above a node here. And I have a similar case for all of my nodes who have an input of 1. Those are also a base case, right? Because the first number of the Fibonacci sequence is exactly 1. So we'll also fill in those 1s above. Cool. Now that I have some floating return values, I can start to reconstruct my larger problems at hand. So let's stay focused on the left-hand side of my tree. Let's look at this particular node. So I'm looking at this node of 2, and I have a left-hand value and a right-hand value ready to compute. I know that if I look at this node of 2, it's trying to figure out what's the second number of the Fibonacci sequence. And so at this node of 2 in blue, what I can do is just take the sum of its children, right, of those green values. So 1 plus 0 gives me 1. And if I do a quick sanity check, that must mean that the second number of the Fibonacci sequence is exactly 1. And this pattern continues up the tree, right? At this node of 3, I take the sum of the 1 plus 1, and I get 2. If I do a quick sanity check, that must mean the third number of the Fibonacci sequence is 2. What we're doing right now is really stepping through how a recursive code would actually return, right? Return means return to your caller, right? So return to your parent node. And so we'll fill in the rest of the values over here. And bear in mind, as you kind of draw out these diagrams, maybe for yourself, hopefully on pen and paper or even on a whiteboard, it's really important, at least for me, that you check for correctness as you build the tree. So if you're in an interview, it really helps to not just check for your top level answer being correct, but at any points of your trace, you should have logical information. In other words, by just looking at this node, right, I have a blue node of 3 over here, whose return value is 2, that logically implies that the third Fibonacci number is 2. And that's totally correct, so I'm good to go for now, right? It would really be a drag if I kind of sketched through this entire drawing, only to realize I had a little typo or miscalculation somewhere below in the tree. So I highly recommend that you stay very aware of your subresults as you kind of trace through a diagram like this. So let's continue to build up these subsolutions. So I know that this node of 2 is going to take the sum of 1 plus 0. That gives me 1. Then finally, at the parent of 4, it's also going to take the sum. So 2 plus 1 is 3. And that must mean that the fourth Fibonacci number is, of course, 3. So let's speed this up a little bit for every other node in the tree. So we're going to add all these up, so on and so forth. Now at the tippy top, we see that this node of 6 at the root is going to take the sum of 5 and 3. And of course, that gives me 8, which is exactly the punchline, right? The sixth Fibonacci number is indeed 8. And so looking at this pretty large tree, you might realize that, hey, our top level problem was asking for the sixth Fibonacci number, not a very large number in the sequence. However, we had to use a lot of nodes to actually represent that problem, how we broke it down. And that's something really important about this Fibonacci sequence, right? It has a pretty interesting complexity, a pretty large one at that. So let's try to analyze the complexity of this. We know that every node of this visual tree represents a recursive call, right? And so the number of recursive calls I make over here, or the number of nodes of the tree, should roughly represent the time complexity of this solution. You're probably already recognizing that it's going to be a very, very large one. Let's go step by step over here. And so to analyze the complexity of recursion like this, I think it's really important to notice any patterns in the tree. To me, it's all about looking in the tree, right? I can kind of figure out at least the ballpark of the time complexity without even writing the code, right? Just using this visual. And so at first glance, you might notice that this one is pretty hard to analyze because the tree is asymmetric. In other words, notice that it's a little taller or deeper on the left-hand side, then toward the right-hand side of the tree, it's actually much more shallow. And that kind of asymmetry makes us feel a little uncomfortable when it comes to figuring out any patterns. So here's what we'll do. Let's actually try to analyze this one by drawing an analogy. So let's ignore this exact Fibonacci tree right now and go for a more symmetric example. So let's say I had a similar recursive code that had a more symmetric recursion. So let's say I had some top level call with a value of 4. And let's say that this top level call to 4 actually made 2 more recursive calls, but both on a -1. In other words, the left child is the same as the right child, which is different from our classic Fibonacci, right? Fibonacci, our left was -1 and our right was -2. But now I'm just doing -1 on both sides. If I continue that pattern, that should give me a nice symmetric tree. Now let's say I had some base case roughly when my value is 1, so I can stop building the tree from here. And so this has a nice symmetry to it. Let's try to notice any patterns now. If I look at the different levels of this tree, let me look at how many nodes there are across a level. So for example, my very, very top level, and there's 1 node on that level. On the next level, there's 2 nodes, and then 4 nodes, and then 8 nodes. And you can probably see how this pattern scales, right? If I drew more of this tree, let's say I had a farther base case, it would be 16 nodes, and then 32 nodes, and so on. And so you probably realize the obvious pattern here, right? At the very top, at the root of my recursive tree, I have 1 node or 1 call, and then from one level to the next, I double it. I multiply by 2, right? And I do this process basically for every level of this tree. So that begs the question, how many levels are there in this tree? Well, just looking at this kind of particular concrete example, there's definitely about 4 levels, right? And I can kind of understand how to designate each level by just looking along this left-hand path, right? So colored in yellow, notice that I have 4, 3, 2, 1. That's just a decreasing pattern. So when it comes to the number of levels, it's pretty obvious to me that it's exactly n levels, right? If my top level problem at the root is where n equals 4, then I have, 4 levels, or in general, n levels. So it's pretty clear to me that when it comes to figuring out the total number of nodes in this tree, which implies the total number of recursive calls we make for this kind of toy problem, it looks like I would multiply 2 by itself n times over, which is a definition of an exponential 2 to the nth power. Cool. So maybe you're a little bit skeptical, and here's where we can either, really buy into kind of the big O complexity, or we can get bogged down by the finer details. Something that you might fall into sometimes, but you have to kind of be very aware of it, is big O is really just an estimate. So if you actually plugged in some values here, you might notice, all right, if I did 2 to the 4th power, right, because 4 is my n in this particular example, that would be 16. And so if we actually counted the quantity of nodes in this visual tree, it would not be exactly 16. I'll label them over here starting at 1. There's actually going to be 15 nodes. So it's off a little bit. But if we, understand big O complexity, we know that if we have something that's of the shape of like 2 to the n minus 1, we can ignore the -1. And what's more is, even if it was off by like 5, right? If it's a -5, that's still a constant that we're subtracting. That still is dropped from the big O notation. So overall, I would consider this particular example as having O of the 2 to the n runtime, which would be exponential, pretty slow, right? So while we're here, looking at this symmetric example before we hop back into Fib, let's try to recognize what the space complexity is. We know that the space complexity for recursive code is going to be more or less the number of stack frames that we use, right, for our recursion. Because whenever we make a recursive call, that information has to be stored on the call stack, right? As we kind of make different function calls and also return from function calls. And so this is actually something I notice students have quite a difficult time analyzing. And so what I'm going to do is really trace through how we would make these recursive calls, as well as how to visualize the call stack, right? So this top level call of 4 would be added to the stack, right? So stack will be just a little rectangular block, right? And then as I make recursive calls, let's say now I call upon 3 as my input, that's also added to the stack. Notice that it's added on top of the 4, right? And really what we have to recognize here is every time we make a call, we're adding a new stack frame, and we only get to remove something from the call stack when it returns. So far, none of my calls have returned, right? Until I have 1 at the top of my stack. Right? At this point, I've kind of bottomed out at like a base case, so I can return from that call, which also means I remove it from the stack. At this point, I need to evaluate 2's right child, so I make another call to 1. And this process continues, right? Now I'm done with both of 2's calls, so it can return. Now I'm back at 3, but 3 has to call upon its right. And the same thing happens. What you'll notice at this point is, although there are many different stack frames we would have to eventually push onto the call stack, at any point in time, there's only about 4 different stack frames on the call stack, right? It's not as if that we store like all of these different stack frames simultaneously, right? It doesn't really make any sense. To add certain stack frames, you must have returned from other ones. So it's actually the case that the space complexity due to the call stack would just be O of n. Overall, we're looking at an exponential runtime and a linear space complexity. All right, so for this particular symmetric example, it has an exponential runtime and a linear space complexity, but how about for our actual Fibonacci tree? We know our Fibonacci tree is more lopsided. It's roughly going to be like half the size of that, and you can take my word for it, it would actually be the same big O complexity, right? It's still 2 to the n, and then just an O of n space complexity. And so, kind of taking a lay of the land over here, the space complexity seems reasonable, right? However, whenever we have an exponential, usually that's not good enough. And there is actually a better or faster way to solve this one recursively, which is what I want to expose us to right now. So let's go back to the recursion tree for our fib problem, right? And so what we can do is try to recognize any patterns within this tree. Do you notice any duplicate work, right? And this is all about understanding, what this diagram represents, right? Every node I have drawn in here with its corresponding number represents a problem. And you can see I have many duplicate problems. So for example, if I look at this subtree, that subtree represents a subproblem, right? Rooted in 4. So I'm asking for the 4th Fibonacci number. Not only do I need to calculate that on the left-hand side of the tree, but at some other point down the line on the right-hand side, I need to calculate that same exact subproblem, right? These 2 subtrees are identical, and they both represent the same problem, the 4th Fibonacci number. And this pattern actually applies recursively because this strategy is recursive, right? So you can notice probably some other different duplicate subproblems, right? If I root myself at 3, I have to calculate this subtree 3 different times, right? And notice that that 3 subtree is also internal to the fib of 4, so it's really duplicate. And there are a few other duplicate subtrees you can recognize over here. So we have a lot of duplicate work in this kind of brute force recursion. And if we actually store some subresults, then we can forego having to recalculate any of these subtrees down the line. And so really what we're looking to do is kind of prune out some branches of this tree to avoid some duplication. So what I'm going to do is kind of ignore this right-hand tree of 4. I'm going to take that out because I would have calculated it on the left-hand side somewhere. And I'll do the same thing for this kind of middle tree of 3. So I can ignore that as well. Cool. Likewise for this too. And so at this point, we don't really have any full duplicate subtrees, right? I kind of took them out of my drawing. So if we actually store some results as we calculate these subproblems, this really represents all of the recursive calls that we'll have to make, right? And so you're wondering, how can I actually implement, that kind of pattern in my code? Well, it's all about just storing some additional information. So let's step through still fib of 6. So I want the 6th Fibonacci number. In the long run, we should get 8. And the strategy I'm introducing right now is called memoization. And so when it comes to implementing memoization in your language of choice, it's all about storing some additional data in a memo. And your memo is typically going to be your hashed data structure. So it could be like a hash map or a dictionary or object, depending on your weapon of choice here. Right? It's really important that I choose some data structure that gives me an O of 1 lookup time, right? So usually that would be your hashed data structures, whatever that is in your particular language. And so let's step through this one again, but now we're going to store some data inside of our memo. And so we have the same base cases as before, right? We know that the first Fibonacci number is 1 and the 0th Fibonacci number is 0. And when these values return to the parent of 2, we're still going to calculate the sum over here. So 1 plus 0 is just 1. But now that I have this result, I can store it in the memo. So I'm going to make the key represent the input to that node or that recursive call, and then its value is going to be that return value. And so if I look inside of my memo, it's a reminder that the second Fibonacci number is 1. So we'll continue this process. I know that I have a base case over here. It's still the case that the first Fibonacci number is 1, and I return to the parent. I calculate that, hey, the third Fibonacci number is 2, and I'm going to store that in my memo as well. And here's where things get a little more interesting. If I look at this node of 2 over here, I've actually calculated this subproblem before, right? I can check that by just looking inside of my memo. My memo says, hey, the second Fibonacci number is 1, so without having to recurse and build the full subtree once again, I'll just go ahead and fetch the stored value in my memo. So I'm just going to jot down a 1 above this node of 2. And I can return to my parent, and I figure out that, hey, the fourth Fibonacci number is 3. And of course, I want to be sure to return that, but also store it in my memo for the future. And same thing happens at this 3 node, right? This 3 node is, again, in my memo. So without, recursing through my tree, I'm going to just fetch that value from my memo. Right? I already know that, hey, the third Fibonacci number is 2. And so I can calculate the value at my parent, right? Fifth Fibonacci number is 5. Be sure to store that in your memo, and so on and so forth. By the time we get to the very top of our tree, of course, we have the fact that the sixth Fibonacci number is indeed 8. And I avoided a lot of the duplicate recursive calls. So it's clear to me that we avoid a lot of duplicate work, but what exactly is the runtime now, right? And so we'll try to notice some patterns. So this visual tree represents our Fibonacci recursion after we implement this memoization strategy, right? I'll try to generalize it over here. So I'll kind of tidy up these edges over here. And let's say I increased the size of this problem. So instead of fib of 6, what if I asked you for fib of 7? That recursion tree would look something like this, right? Notice that the root is now 7, of course, and it's still the case that the left child is -1, so a 6, and the right child of the 7 is a -2, or a 5, right? Still obeying the rules of Fibonacci. And I only added 2 more nodes. If I increase the problem size to fib of 8, I would still add 2 more nodes. So every time I increase my input by 1, I only add 2 nodes. It's always adding a constant number of nodes. At this point, our problem scales linearly, right? In general, we're going to notice that we have basically 2 times n nodes. And notice that that's not 2 to the n, right? I'm saying 2 times n. And so we can simplify that to a runtime of O of n. And the space complexity is still the same, right? Notice that the space complexity for this algorithm is really just going to be the height of the visual tree. It still looks like a linear chain, right? If I go along the left-hand path, it just goes 8, 7, 6, 5, 4, and so on. So definitely an O of n space complexity. And this is actually a pretty efficient solution for our Fibonacci. And so I think from this point, let's go ahead and implement this in some code. That way we can have this core pattern under our belts. So I highly recommend that you try to implement this one in some code on your own. But don't forget, we also have the video walkthrough available if you get stuck or just want to code along.